Thank you, Mr. Chairman, for your gracious introduction. I am honored here to have a chance to address you on this special occasion. Firstly, I want to introduce myself and my institution. I am a PhD student from Southeast University, and I am currently focusing on the research of RF MEMS devices, such as particularly the microwave power sensors and frequency sensors. Okay, let's move to the topic of my today's presentation. My topic is modeling of an inline MEMS frequency discriminator for RF receiver front-end application. My presentation will include 4 parts as follows. First, some background information about this research. Second, the principle of the inline MEMS frequency discriminator. And third, the application in RF receiver front end. And last, some conclusion we have got. Well, let's move to the first part of my presentation. As we all know, the modern communication systems requires low weight, volume, and power consumption, and a high level of integration with electronics. And are radio frequency components fabricated by the microelectromechanical systems technologies, such as MEMS switches, MEMS inductors, MEMS phase shifters, and MEMS resonators are widely utilized in today's wireless communication systems. Look at this picture. This picture shows a sketch of a traditional RF receiver front end, and as can be seen, it consists of an antenna, bandpass frequency selected filter, an a mixer, IF bandpass frequency filter, an IF amplifier, and an AD commenter. And the VCO produces a local oscillation signal to the mixer. However, in this traditional RF receiver, there are 2 disadvantages. The first one is that the frequency of the RF signal we received from the antenna is unknown, and this will increase the design difficulty of the lateral filters. And the second one is that the control voltage of the VCO is introduced by an additional voltage source. So my paper mainly solves these 2 problems. So how to solve the problem? And our group has presented a novel inline MEMS frequency discriminator for this RF receiver front-end application. As can be seen in this picture, when an RF signal transmits on this CPW transmission line, a certain percentage of the microwave power will be coupled by the MEMS memory, and then fed into the 2 thermoelectric power sensors. And the thermoelectric power sensors will convert this coupled microwave power into a DC thermal voltage. And if we use this DC thermal voltage to control the VCO, and then we can avoid the additional voltage source. And what's more, the MEMS memory has a different response with different frequencies, and so it can also realize the inline frequency detection. Let's see its working principle. According to the equivalent circuit we have shown, in this picture, we can calculate the coupling factor as these expressions show. And based on this coupling vector, we can calculate how much the microwave power has been coupled by the memory. And because the coupling power is dissipated by the thermal resistance, which will produce heat around the thermocouples. And so we also need to talk about the principle of the thermoelectric power sensors. And based on the seeback effect, the thermoelectric power sensor will convert thermal energy to electric energy, which is shown as a DC voltage, VTH, as this expression shows. And we substitute the above calculated coupling vector into this voltage VTH. And we can find the VTH has a quadratic relationship with the incident frequency. And then we use this VTH to turn the VCO, and the final resonant frequency of VCO can be turned by this equation. Next step, we establish an equivalent circuit model in the ADS software. Results shows the simulated DC thermal voltage versus frequency and time domain. As can be seen from this picture, the DC thermal voltage increases with the frequency and becomes stable after 400 nanoseconds at time domain. And furthermore, we also fabricated this inline MEMS frequency discriminator by gallium arsenide MMIC technologies. This is the corresponding SEM photo paragraph. And the measurement results show that the return loss is less than minus 15.2 dB from 8 GHz to 12 GHz, while the insertion loss is better than 1.18 dB. And for power measurement, the picture shows the measured DC thermal voltage versus frequency and input power, and we can see the DC thermal voltage has a nearly linear relationship with the frequency. And when frequency increases from 8 GHz to 12 GHz, the DC thermal voltage increases from 1.27 millivolts to 1.49 millivolts. Well, as for now, the whole RF receiver front end with the embedded inline MEMS frequency discriminator has been obtained, as this picture shows. And based on the above analysis, we can see it can realize the inline MEMS frequency detection of the RF signal, and also the outputs, the control voltage of the VCO can be turned by the DC thermal voltage, which is generated by the two thermoelectric power sensors. So a complete simulation of the whole RF receiver front end is conducted in the ADS software. For example, we introduce 10 GHz signal for input, and after IF modulation and demodulation, a 60 megahertz IF signal is obtained. This means a 60 megahertz tuning value of the VCO, and the spectrum diagram also proves the tuning ability of the VCO. Well, this will end my presentation, and let us see what we may conclude here. My work concentrates on the modeling of an inline MEMS frequency discriminator, which is applied to the RF receiver front ends. And this inline MEMS frequency discriminator has the ability for frequency detection, and the frequency band focuses on X band. And in addition to the frequency detection of the signal, the resonant frequency of the VCO can be tuned through the output DC thermal voltage generated by inline MEMS frequency discriminator. Okay, thank you very much.